Ma'am, you can share your screen and start the session.
Okay, sir.
Okay, thank you, ma'am.
Yes.
Yes, your screen is visible. If possible, please just make it in full
Yes.
screen mode.
Yes.
Yes, it's perfectly
Okay.
visible. Thank you, ma'am.
Okay. Thank you, sir. Yes. So, good afternoon, everyone. So, we already had our 4 lectures where we covered a few things, starting from a bit of like classical to quantum transition, why it was very required, what are the areas where there we can see a bit of challenges with the computation as well as with the time, security, space, all those things, and simulation disability that we have. Not that much of like flexibly we can enter into the nanoscopic level, all those things we have seen, followed by a few theoretical principles of that quantum physics, which was a fundamental or core building blocks for quantum computing. We have seen those things. Then a few of the like quantum mechanical principles we had learned already, or at least we had an initial idea about it, which is say superposition, entanglement, bit of no cloning theorem, interference. These 4 properties we discussed. So today we will actually, and obviously after that we have seen fundamentally what a qubit is in our previous class, and then the difference between a classical and a quantum state representation, all those stuffs we already have seen. So now from today onwards, today also we can say we will spend some more time on these postulates as well as few of the things. Slowly we will understand the concepts of computing in a bit detailed way. I hope that I can complete the basic quantum gates as well today, so that we had a building block to go for the quantum circuit design and algorithm. So that is kind of a plan that I have. So so plan is pretty much like this, that by say because we have today we have a 2-hour session, tomorrow also, Thursday. Thursday also, yes, that is tomorrow. Friday we have a 4-hour session, that is on 8th, and Saturday or Saturday, I guess Saturday we have a 4-hour session. So by that time what I want is, because you have an exam on 9th, so by 8th I will try to cover fundamental of quantum computing, physics, whatever we have completed, considering that, keeping that, plus a few of the quantum computing stuff, the quantum gate, quantum circuit, quantum algorithm, brief of that. That was our plan. That is my plan actually. On 9th, I have only 1.5 hour session with you, not a complete 2-hour session, but you have an exam, your exam post my class. So on 9th, I will be covering the hardware parts of it, which will not be included in your exam for this 9th exam, because we will be having class on 9th. So after that only you have a new exam. So that 1.5 hour I have thought to put on the quantum technologies part, a bit of what are the possible qubit architecture and configuration. We will be discussing a brief, because those are very theoretical. So we will be discussing about those things, will not be included in your exam. And after that, 10th, 11th and 12th, these 3 classes we will be discussing about quantum cryptography and communication. So maybe if time permits, because we have a like small thing for a quantum error correction as well. So depending on how much time is left on those 3 days after post the communication and cryptography part is over, if some time permits, maybe 30 minutes or 45 minutes, I will put for the quantum error correction. And one quantum error correcting principles also we might learn. So that is kind of your association with me for whatever syllabus I am going to cover, a brief of that kind of a curriculum that we have. So keeping our these curriculum in mind, I will design the respective classes till 8th. Okay, just remember that. So Bhavna, I think you can just post your question, or it is by mistake. Please check. Okay. So and please focus on the theory, bit of theories. Maybe some of you asked that what kind of an exam, what kind of questions we might have in our exam. So what can we will discuss at the end of today's class only. Okay. So it will be a blend of theory. It will be from theory. It will be MCQ. It will be multiple selection questions, or also that can happen instead of only choice. So maybe more options will be correct. You have to tick that. And also, if possible, I'm trying to put at least 2 to 3 numericals, uh, which will be definitely will understand from what are the areas and what kind of a numericals will come. So either it will be a numerical answer type question where you have to put your value, or it can be some MCQs where you will have to calculate a certain value. Then you have to put that value. For example, whatever kind of an example we have seen, say yesterday and today and all these days, because numericals wherever it had entered till 8th, whatever we will study, all can come in the exam. Okay. So that is the plan. Now let me start. So the Moore's law, it was very fundamental when the quantum thing evolved. So it says that the amount of information that we can store on a given amount of silicon has roughly doubled every 18 months. Now you can imagine that we have a like more of a, instead of a transistor size, the information itself is going to a like explosion, at the level of an explosion, wherever we are standing right now, with the big data and all those stuffs coming into picture. More data we need to fit in, and more data means more, at least data processing will also increase, data interpretation, all those things will increase, data extraction. So this data also is another challenge that was a kind of reason for quantum to evolve. Just remember this Moore's law. It was very, very important when we thought of transitioning from the normal transistors, that the classical building blocks, to the quantum resistors and all those stuff. So we definitely needed for a change. And Feynman's suggestion, it was the instead of regarding like computers as devices working under the law of classical physics, which is very common sense, let us consider their operation as a special case of more general theory, which is governed by quantum mechanics. And I told you that quantum definitely covers classical, but it is beyond classical, something beyond classical. So our classical way will fail. And this was a suggestion of Dr. Richard Feynman. And he's also thought of like a father of quantum mechanics and something. Okay. So requirement for new computation, all these things are for your reference, at least for this exam. Just go through the slides, is very basic one. A sequence of events. Feynman proposed the idea of creating machines that are based on quantum mechanics instead of the laws of classical physics. It was on 1982. And okay, on top of that, I think I can safely say that nobody understands quantum mechanics. So it is very true. Nobody can really understand it. And if he says this, definitely we have to believe it. But jokes apart, it is just that understanding everything at a nanoscopic level is very difficult. Even if we have certain quantum simulation, it's like it is so random, it is so non-deterministic, so you cannot predict that. And also there is a theoretical backup for the statement. If I have to find an alternative interpretation of whatever he meant to say is, say when we can predict something, when we have a certain, while we are preparing something, if I know that what are the constituents and how I prepared it, what is the recipe, then I will be able to tell it at the output. Okay, this I should be getting. I'm cooking, for example. So if I know that what are the ingredients and in what sequence and how much I put into my meal, I can definitely at least predict its taste, whether it's going to be sweet or sour, or what exactly, how much sweet and how much sour. And there is another way. If I say I'm testing a certain food, do I able or will I be able to tell that okay, this might be these might be the ingredients that might be required for building that recipe? Yes, at least I can predict it. So I have to fix at least one. If I have to predict, either it should be like at the preparation level or it should be at the measurement level. So that contextuality or that much of information should be there with you. But a perfectly quantum system is neither, it's a non-contextual in both the senses, right? So you cannot tell that exactly what will be your measurement, or you cannot tell or exactly what was your preparation, or why I'm telling, maybe because you're preparing something at the some physics experiments you are doing. So after a certain experiment, it will not change during that time, or the deviation will be very less. But here, the deviation, whatever will be the deviation, we're trying to measure that itself. So that is very difficult because the deviation is in nanoscopic level, say, for example. Now, in quantum, it is like that. So all the principles of quantum physics, just remember that. So it is every minute level how the behavior changes. That is quantum. So we have to now think quantumly, and that actually tells that, okay, so we cannot actually predict how a quantum mechanical system will exactly within double quotes behave like under a perfectly noisy environment that a quantum computer might be into. Okay, noisy does not mean that pressure and temperature can be anything. It has to be suitable. Noisy means that it will be like open to the quantumly interferences that can happen to it. Maybe caused by another qubit, maybe caused by decoherence. So quantumly also there will be a certain interference that can affect its behavior, right? So that was the meaning of it. So 1982, it was the proposed, he proposed the idea of creating the machines that will follow the laws of quantum physics. Then 1985, Dosh or Deuce, whatever you call it, he developed the quantum Turing machine showing that quantum circuits are universal. That is, from a quantum circuit, you can actually devise any other circuit that he showed. And then 1995, Peter Shor. Then 1994 is that time when in algorithm, quantum algorithm, on the real essence, the computing essence, something like extraordinary happened. It was because of an MIT mathematics professor called Peter Shor. So he came up with a quantum algorithm to factor very large numbers in polynomial time. Okay, and initially it was in exponential time. So he, for the very first time, has shown quantum supremacy, where he showed that it can be like an exponential speed up that can be offered by a quantum computer rather than a classical, what you had in a classical setup. So the exponential speed up concept took place in 1994, and he shown, like Peter Shor, he showed that we can actually break the RSA crypto system. Okay, it was his idea, his algorithm, everything. And on 1997, another scientist called Love Grover from the same MIT, who was also a student of Peter Shor, he developed another like mind-blowing quantum algorithm, which was for a unstructured database search. So he showed that, okay, even if you do a, say, unstructured database, I have not a like sorted one. So if for a sorted database, for a sorted array, the time taken would be in order of log n, right? But if I have an unsorted one, considering that no hashing and all those things I'm doing, that is, I'm not doing anything with the space. I'm not adding space into it. So it will ultimately be order of n in the worst case. If I have an element, if I have 10 elements in an array, which is and I'm applying linear search, considering my array is not sorted, then in worst case, it will take n minus 1 number of comparisons, which is nothing but big O of n, or like omega big O of, yes, big O of order of n. Okay, so he showed that I have a quantum algorithm through some quantum logic. It is possible for even an unstructured database to find an item which is called a needle in a haystack, say, in order of root over of n complexity. Now you can imagine this is a quadratic speed up that he actually offered. And all the SQL and all those things, what is the most promising kind of query? That is the when we actually do the select query. Right. So these are the queries which is maximally like done instead of the data manipulation things. Absolutely, it is a root over of n that you can do. And he showed it. If time permits and if I can show something of it, then I will tell you that how to design that quantum circuit. That is what I'm planning. Maybe on 8th or say 7th to 8th, somewhere in between, we will be covering those things. Okay. So he showed that only in root over of n number of queries, you can actually search a unstructured database. Perfectly, you can find the item. So what is a quantum computer? I will not tell, but I will just highlight one point. Just see the last point. That is classical HPC, or a high performance computer with a gigahertz capacity. Gigahertz means 10 to the power of 9. Okay. cycles per second. So this capacity will take about 317 trillion number of years. Trillion means 10 to the power 12. So 317 into 10 to the power 12 number of years in order to break a 2048-bit RSA key, which also offers very less amount of security. I guess it's for 80 bits of security level that 2048-bit RSA key offers. Okay, even for that, for a high performance computer with gigahertz capacity will take 317 trillion number of years. On the other hand, a quantum computer, that is why RSA, we think that RSA is very safe and secure, and in every security applications, we are relying on RSA. But this is not going to be the story after 20 or 30 years from now. Even right now also, everything we want to transition to post-quantum or quantum safe cryptography that will not rely on RSA, that will rely on something else. We'll see these things on 10th, between 10th to 12th. But on the other hand, a quantum computer of megahertz capacity only, that is a 10 to the power 6 cycles per second, that it can do the same task in only 10 seconds. Now, if you make it like, if you increase the capacity of quantum computer even more, then it is going to take even less amount of time. Okay, so that is the power that quantum can bring into picture. And that is the threat also that quantum is bringing into the picture. So it's basically for a classical computer, it's order of n but still all sectors rely on AES ECC encryption. Not really, they are relying because quantum computers are not that much of an mature enough to fit into it. I have told you, like, whatever we are doing right now in terms of a logical qubit, but whenever on the implementation level, you have to think that how many physical qubits are required in order to cope up with the decoherence and all those kind of hardware challenges that it has. Okay, so for that thing, we are currently relying on this. But Shor already broke RSA for a prototype level. The algorithm is ready. Everything is ready. The encoding, the entire process, or say Oracle, that is ready. What we need is just a few, a more capable, a more resilient kind of a quantum computer, which has a minimum error rate so that it can break RSA. So we all are working on that. So all the public key encryption algorithms, like the AES is not encryption like public key. It is a symmetric algorithm or a shared key algorithm. But all the public key algorithms, like say RSA, then ECC, elliptic curve, then digital signature algorithm, DSA, all are in equal thread because all rely on the same algorithm or the same principle, which is basically RSA is following. By the term oracle means, as of now, you can think it of and just like an operator, which is a black box to you. So you don't need it. Once you have a Shor's algorithm ready, you give your data, it will be able to break it. So oracle is any computing kind of model which is a black box to you as of now. You can think it of like an oracle. Okay. Oracle is not really very specific to quantum thing. It's a normal like language that we hear from. Concept between the show, that is important quantum postulates, superposition, entanglement. I want you to refer to these things for your exam and for the theory purposes. Okay. So someone in the maybe second class mentioned that can you just explain the cat experiment? After day one, I'm unable to get the recording even. Okay, please refer. Please just refer your host, whoever from where you can get that one. Okay, because I also do not have any access to those things except say YouTube. We can check. So superposition is the cat experiment. Says it was a very fun experiment. It had nothing to do with the mathematics and all. So it is just that, say for example, I have a box which I cannot open, and within a box there is a cat. Now, without opening it, can I tell what is the status of the cat, whether it's alive or it is dead? I cannot tell. But is there any possibility that simultaneously the cat can be either alive or dead? Because I do not know. So cat may be alive or may be dead. But once I try to open the box, what I will see exactly the one status of the cat at that time. Either it will be alive or it will be dead. So remember, so just identify here that it has a possibility to be alive and dead at the same time. That is, it is in superposition. What is in superposition? The two states are in superposition. What are the two states? Alive state and dead state. So cat state is equals to, with a certain probability, times alive state, say cat alive, plus certain probability, again say beta, probabilistic amplitude say beta, times cat dead, within a cat dead. That was this cat experiment, Schrodinger's cat experiment. And once I open it, that is, once I measure it, I will be getting exactly 1 as an output. Either the amplitude associated or the probability associated with alive will be high and other will be 0, or dead will be high and other will be alive will be 0. That was the experiment. So just follow the picture. In classical states, either it will be, say, outside the box is 0 and 1 is inside the box. So either it can be 0 and 1. But quantum superposition means it can both be outside as well as the inside one. Okay, so it's a 0 and 1 together. It will be like, it will be present. Okay. Entanglement concept, are their direction same or are their direction different? I told a bit more mathematically, like a correlation and anti-correlation stuff. While we'll be doing a certain quantum circuit, we will see that entanglement can actually be visualized. You can see the effect of entanglement. There is a 0, 0 and the 1, 1 thing. And quantum entanglement in computing is actually when we have certain kind of a quantum system between two qubits. So we call those two qubits as entangled when exactly the behavior, or the half of their behavior is in a one way and half is being controlled by the other way. So we call, at that time, it's a maximally entangled pair. For example, say I have something like 0, 0 plus 1, 1, or say 0, 1 plus 1, 0. So these are the things when we call it a maximally entangled pair. But there can be entanglement in other way as well. We can establish a certain entanglement that when it will be, say, 0, 0, 0, 1, it is also entangled. We can do that. We can establish entanglement in between multiple qubits through certain kind of a quantum gates. But when it is absolutely in sync, we call it as a maximum or maximally entangled pair. We call that one. Say 0, 0, 1, 1, these are maximally entangled pair. Now, quantum bit, a bit of data that is represented by a single quantum state, or it can be denoted by a combination of 0 and 1 as well. So a qubit or a quantum bit can hold anything. A qubit can be either 0 or 1 or a combination of 0 and 1. A qubit itself can be either in a pure state, either 0 or 1, it can be in a superposed state as well. Okay, so that alpha, or say for example psi equals to alpha ket 0 plus beta ket 1 might represent the qubit status. So either it can be 0, that is also the same qubit, or it can be 1, that is also the same qubit. Just remember that alpha ket 0 plus beta ket 1 does not mean that 0 and 1 are two different qubits. Okay, so one qubit, say 0, on certain operation can become a combination of 0 and 1, which we represent through alpha ket 0 plus beta ket 1, but both are qubits only. Both are qubits. So only ket 0 is also a qubit and 0 plus 1 is also a qubit. These are not two different qubits. This is what I am trying to refer. It's a qubit in superposition. Yes, it is a qubit in superposition, but it's single qubit. And only only say 0 or ket 0 and 1, they are also qubit, but which are not in superposition. So they are in a pure state. Yes, the same things are written over here. Only one case, one small error that is there in this slide. So only it is written that alpha 1 plus alpha 2 is equals to 1. So it just will be alpha 1 square. That square is missing here. Just keep a note for this slide. It will be alpha 1 square plus alpha 2 square is equals to 1. Yes, alpha ket 0 plus beta ket 1 is a single qubit. That is what I am referring. But it is not a pure qubit, but it is a single qubit. So superposed qubit does not mean it's multiple qubits. Superposed qubit means it's one superposed qubit. For example, say whatever you can see on the right, say phi equals to alpha ket0 plus beta ket1, it is also one qubit, which are in superposition. Okay. Can you explain what is a quantum state? Okay, I explained already because it will take a lot of time. Please refer a day 2's class. Quantum state and the number of quantum bits and how they are related. What do I mean? One system can have how many qubits determines the number of, like, how many states should be there. All these things I already had explained. Just refer there once. As of now, you can remember in this way. In very easy words, if I have one qubit, I will be having two states, ket0 and ket1. At least these two states I will be having. If I have, say, two qubit, then I will be definitely having four states. So 0, 0, 0, 1, 1, 0, and 1, 1. These are the four states. Now, you might ask me that if this is the four states, is it in superposition? My answer is no. 0, 0, comma, 0, 1, comma, 1, 0, comma, 1, 1. These are four different quantum states. But if I write that phi is equals to, say, 0.25 or root over a 0.2, whatever it is, the amplitude, forget about the amplitude, but phi is equals to alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1. Now, if I ask you, is it a quantum state? The answer is yes, it is also a quantum state. But how many qubits here I have? I have two qubits. The probability amplitude will never be greater than 1 because of the normalization like constraint. It can never be greater than 1 because its square will only be is equals to 1. Okay, I hope it is now clear. You might be asking me question because of this. Say phi is a quantum state here, but you can see in the slide. Phi is a quantum state. It is one superposed qubit state, but only one qubit is there. If I have two qubit, then only it will be 0, 0, 0, 1, 1, 0, 1, 1. But if I write it in a superposed way, then it will be 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 with alpha, beta, gamma, delta, whatever. That I will put in, say, phi again. So that phi will now be one state which is in superposition or a one superposed state, but that superposed state comprises of two qubits, not one qubit. So that is the difference between the state, superposed state, and the number of qubits. So one quantum state can also be like phi is equals to, say, A1 0, 0, 0 plus A2 0, 0, 1 plus A3 0, 1, 0 plus dot 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 A7 or A8, whatever it is, 1, 1, 1. So it has three qubits. So it is a 3-qubit system, but it has only one superposed state, which is the all the 0, 0, 0 till 1, 1, 1. But how many pure states here you have? Individually, when you started with say initially just before like the superposition, it was 8 pure states. So you added up 8 pure states and make it a superposed state. But how many qubits you have? How many qubits you have? 3. Okay. Yes, absolutely. So this Hilbert space and inner product space, I discussed it. Just go through it. Okay, just a few things. So just check a few things. Yesterday I was telling it, it's better to show it mathematically as well. So initially, say for example, A and B are two elements that belong in a two-dimensional complex space. Complex vector space, and in quantum every vector space or every like inner product space is known as a Hilbert space. So I can definitely I can toggle between telling you it's a like a inner product space or it's a Hilbert space. It shouldn't matter to you right now. Okay, so it's a two-dimensional complex space or known as a Hilbert space, where say ket alpha is basically the column vector form A1 and A2. Bra A is basically the row vector form, which is A1, A2. Or say bra rotation with B, the element B will be B1, B2 in the row vector form. I can also write it in this way. That's a ket vector form, and on top of that, as a superscript, it is a this conjugate symbol. So I can actually both, because they are dual or conjugate, so I can actually use that thing. Krishna dagger. Yes. Yes, you can also tell it dagger. Is my voice breaking or any issue with the voice? No. Thank you. Thank you for confirming. Thank you. Thank you. Okay. So it's a dagger or a conjugate, whatever you call it, you can call it. So just see that the Ket notation and Ra notation, you can alternatively write in that way. Also, it is often represented with a certain kind of a star. So all these meanings are equivalent. All these meanings should be equivalent to you. Don't get confused with the symbols. Just remember what they mean in the matrix level. If you understand that, then ultimately everything will boil down to the final representation only. Now, if they want to call it anything, it shouldn't matter to you. Now, if I tell bracket notation together, okay, so with B, so bra B and kit A, when represented in this way, it's basically the inner product form. Yesterday itself, we have seen that this type of notation is called the inner product form. Right? Now let us do the computation slowly. So initially, where is it? So initially, bra B was B1, B2, right? So I'm just writing it B1 and B2 star with a star and say A1, A2 likewise. Okay, so it's B1 star A1 plus B2 star A2. So it will be like a scalar product because it's only one value, right? It's only one integer value that you will be getting, or one scalar value. But with that, if you say do this thing, say ket bra, then it will be first ket A, then bra B. So it will be like A1, A2 in the column vector format, followed by the row vector form of bra B. So if I do this, of course, it is a 2 cross 1 matrix and it is a 1 cross 2 matrix. So result will be what? Result will be a 2 cross 2 matrix. So this is the outer product form and this is the inner product form. So inner product form always gives you a scalar, which is this thing, and outer product form always will give you a matrix. Now in exam, you might be having questions like, that is the interpretation, that it will ultimately yield to a scalar form and it will yield to a matrix form. That is the interpretation that we will be using. Depending on our operators or what do they mean or how to compute it, we have to choose what kind of notations we are using. But mostly it's always a Ket notation, I've told you. Mostly it's always a Ket notation that is used in order to represent a state because of the ease of the matrix multiplication. Why? Because operator is a matrix multiplication. First of all, quantum gates will be applied on the quantum states. Simple. What is quantum gate? It is nothing but an observable. What is observable? It is nothing but an operator. And how the operator looks like? It looks like a matrix. What type of matrix? A square matrix, mostly a square matrix. Now, once that square matrix is applied, say for example, n cross n matrix is applied on certain quantum state. Now, let's focus on the quantum state. So, how the quantum state or the arbitrary quantum state should look like? If it looks like, say 1 cross n, that is a row vector or the bra notation, then the multiplication itself will be very difficult. We cannot do that. So, what we want is, we use the n cross 1 or the Ket notation there. And also just remember, if you remember the time evolution of quantum states, as I was telling, our ultimately, just try to visualize it in this way. Initially, I have a certain quantum state in one form. With respect to time, slowly my quantum state will evolve. That is the essence of quantum computing, right? So ultimately, my quantum state will evolve. So I shouldn't be like doing anything with the structure of that. So what initially it has, that particular form should retain. So it will be again a 2 cross 1 matrix, or say 4 cross 1, 8 cross 1, but just its values, its phase, all those things, those information will change. And for every time while doing this time evolution, how we are actually evoluting or doing the evolution with respect to the quantum states, we are applying quantum gates or operators in order to change the quantum state. And finally, just before measurement, our quantum state will have that kind of a bit of skewed or bit of final representation, where just before measurement it is. So whenever we are measuring it, so that we can get our desired result. Okay. Maybe we need to apply a post processing on that desired result as well, but it will definitely, through some very easy classical post processing, it should be able to give me the output. That is very like not exponential, very, very nominal, say polynomial amount of time it should be able to give me. For certain quantum algorithms, there exists a classical post processing that happens just after the measurement. But just before measurement, our system should actually hold the desired value or the desired kind of features into its quantum state, which we will be finally measuring. Okay. Okay. Now, pure states, say ket 0 and ket 1, which is 1, 0 and 0, 1, they are called orthogonal because the inner product of these two vectors is 0. And if if we have two vectors and if we are asked to check, say for example, that whether these two vectors are orthogonal or not, then what you have to do, you have to check the inner product of those things. Inner product means the first vector that is given. The first vector that is given, you have to make the like a bra notation of it, followed by the second vector. Just multiply them. You should be getting a scalar product. You just need to check whether the value coming is 0 or not. If it is 0, you will call okay, it is orthogonal. If it is not, you will call it is not an orthogonal matrix. The two vectors are not orthogonal to each other. Okay, so for example here, so initially it was ket 0, which was 1, 0 in the column vector form. I have made it up 1, 0 in the row vector form in order to fit into the inner product norms, times 0, 1 in the column vector, just multiplied and it is coming 0. So that is the orthogonality that you might be asked to check. And all quantum states are normalized. Okay, initially, let me go back to again. I have said here, pure states are orthogonal. You can also check it like 1, 0, 0, 0 and 0, 1, 0, 0, something like that. Now, if I tell that it is, say for example, ket 0 is given to you, or say alpha, ket alpha is 1, 0 and ket beta is 1, 1. Now, if you check it, will it ever come to 0? Let me just do it like automatically without using a pen and paper. I don't have access to it. That say 1, 0 in this way and 1, 1. So it will be 1 into 1. Of course, I can see that since 1 into 1 is coming, so it will never be 0. So if a superposed state comes into picture, it will not be orthogonal. Or you can manually check it as well, that if there is any special property, then it will be orthogonal. And all quantum states are always normalized. So just check, that is the same state in the inner product form should always give you 1. For example, say phi is equals to 1, 1. So 1, 1 is a pure state or a superposed state. 1, 1 is what? Phi is equals to 1, 1. What is it? Whether it's a superposed state or a pure state, please give it in answer. Yeah, superposed state. Superposed state. Because in pure state, it can be only 1, 1. All the other values should be 0. So it's a 1, 1. So right now, just try to calculate these inner product form with respect to the same state. If you calculate it, it will be like 2. So phi is not normalized. Psi is not normalized. Okay. But if I have, say psi is equals to 1 over root 2 and 1 over root 2. This thing. Okay. If I have this thing. So what is the meaning of this 1 by root 2 and 1 by root 2? It means 1 by root 2 times 1, 1. I will conclude to one particular observation through it. Please focus once. So 1 by root 2 times 1, 1. Of course, I can write it down because 1 by root 2 is just a constant. So I can bring it outside. So it will be 1 by root 2 and 1, 1. Now calculate the same thing, inner product. Okay. So phi, ket psi and bra psi, all these things for the inner product form. If you do it, it will be 1 by root 2, 1 by root 2 and 1 by root 2 and 1 by root 2. If you now multiply, just check it. So it will be 1 over root 2 and 1 over root 2. In this way, it will be cancelled out and finally you will get a 1. Okay. Now your observation is, you can see that the same thing when it was 1 and 1 in the earlier case, it was not normalized. But right now here, for a 1 by root 2 times 1, 1, it is normalized. So what do I mean by that? Is there any change that you are watching here? What is the difference that 1 is not normalized and this 1 with a 1 by root 2 is normalized? This 1 by root 2 is what we are using to normalize it, because it comes with the probabilistic amplitude thing. So you have to consider that alpha ket0 plus beta ket1, where alpha and beta cannot be anything. You have to normalize it so that ultimately the squares of the and the sum of all the squares of the probabilistic amplitude should be equals to 1, because probability itself can never be more than 1. So in that way you have to normalize it. So it is a normalization constant, it is not constant, it's constraint. Normalization constraint that you have to follow. Okay. So in that way, it will work. Okay. Now, the Hermitian matrix, it is another very well-known matrix. So before Hermitian, any one of you know what is a symmetric matrix and a skew symmetric matrix, or the fundamental of this one? Superposed state and mixed state, both are same thing. Both are same thing. As of now, you can tell that both are same thing. Yes. So, okay. Guru Raja, just a minute. Just wait for a minute for the orthonormal thing. Just wait. So symmetric matrix and skew symmetric matrix is when basically, yes. So the matrix and its transpose is basically the same thing. Then we call it a symmetric matrix. And what is the definition of a skew symmetric matrix? When the transpose of the matrix is equals to the minus of the matrix, say for example. So since you have written A, so yeah, A equal to minus A transpose, or A transpose is equals to minus A. So the concept of the symmetric matrix and the Hermitian matrix is almost the same. Almost the same. Only it is that symmetric works in the cases of only real values, and whenever it's in a complex number or complex space, it will be the Hermitian matrix. Okay, so here also the Aij are the respective positions, like A11 or A23. Likewise, you have to calculate. So A23 will be that thing Aij whole bar. So just check here, all the principal diagonal elements are always real numbers here. Okay. And now just check, say 1 is this one, say 1 2 and A21, that is same. 1 3 and A31, that is same. Only the complex conjugate is here. So whatever is here, say 1 plus 2i, it will be 1 minus 2i. So if it is say minus I, it will be I. That is 1 4 and 4 1 position is always same. It will be just the common conjugate of that one. And also just one thing, Aij will be Aji, then conjugate. I think it's Ij here. So just check it. Yes. So first you have to do the transpose, then conjugate. Transpose conjugate. So Aij is Aji conjugate of that. Okay. And we represent using this kind of a dagger thing. So a dagger denotes a complex conjugate, and if this happens, then it is called a Hermitian matrix. So properties of Hermitian matrix: every Hermitian matrix is a normal matrix. The entries of the main diagonal of this matrix is always real. A matrix that has only real entries is symmetric if and only if it's a Hermitian matrix, and all those things. And also you can check with the eigenvalues of it, and those kind of things also you can check. Okay. This is very fundamental mathematical. So if any questions are asked, it will be taken into consideration that it's very basic and you understand it. Like say for example, the summation of what is a trace of a matrix. So what is a or the trace of a matrix is basically the eigenvalues, summation of the eigenvalues, or the say determinant of the matrix. And what is the relation between determinant of the matrix and the product of the eigenvalues and all those stuff. So these kind of questions might come. So those are very fundamental. And unitary matrix. So in linear algebra, a square matrix U will be unitary matrix if and only if its complex conjugate transpose U dagger is also its inverse. So U dagger U should be equals to an identity matrix. It will always be an identity matrix, where I denotes an identity matrix, and 1 plus I, and all these things will happen. Okay, why we use Hermitian matrices? Because of the time evolution and all those things we do, because of the reversibility, in the matrix itself has to be Hermitian. That is how it behaves. Whenever you do some matrix multiplication or all those things, so if it is not Hermitian, the reversibility property will not be there. And that is why it is unitary as well as it is Hermitian. It is just to not verify, just to confirm the reversibility logic that Hermitian brings into picture. While we'll be doing a lot of like a series of quantum operators working on quantum states, it has to be Hermitian. These are properties you can check. Unitary operators. Okay. So now Bloch sphere. Bloch sphere is, I have the 3D ball that I was referring to. It has a pictorial representation or a diagrammatic representation. It's not any real thing that happens, but it is just, we believe that maybe in a Hilbert space, a quantum states behave like. Okay. And with respect to different axes, we check it. Like the main axis, which is called the Z axis, is the one that is dividing it from the like two halves, the left and the right circle. That's kind of thing. That is the Z axis. And this plane, which is dividing it horizontally into two halves of the like semicircles kind of thing, that is called the XY axis. And this is X and this is Y. So of course, this is the XY plane. This is the XY plane, and this vertical bar, vertical line or axis is the Z axis. Here, one very important point is that every measurement, whenever we do it, it will happen only in the kind of Z axis. Then only we will be able to see it. So if there is any other like with respect to some other axis, if we are measuring a quantum state or trying to get the or fetch the information of its current position, then we have to keep it in mind that ultimately you have to translate it at the time of measurement. At least you have to translate it in the Z-axis format, so that you be able to understand it, and the amplitude and all those assumptions are correct. As and when or the way you encoded it, you get the result in the same basis. Otherwise, the basis itself will change. Just keep it in mind. And if this is the location theta and this is the phase or global phase, that is phi, where phi has basically no such outcome with respect to, yes, because Z axis is the real axis that we believe. So everything ultimately, while measurement, it has to be in the Z axis. It is also called the measurement axis. Why matrices is used in quantum computing? Because all the quantum operators or quantum gates are in matrix form. It is the way it works. And in order to compute something, you need to just physically represent it in some way, and you generally represent it in the form of a matrix. More information about eigenvalues and eigenstates. Eigenvalues of the electric computation. I have not understood, like I have not understood the last one, in dimension computation, that one. Eigenvalues or eigenvectors, you want more like classes on that? Then what I can do is I can just solve a few examples starting from any random matrix and through the characteristic equations and all. Then I can actually share with you. Instead of discussing it class, I can share it. Because I thought it's very normal thing, like what will be the eigenvalue, like considering that you have a matrix A and you want to find, say, a 3 cross 3 matrix you have, right? And you want to find the eigenvalues of that matrix. Then just enough you have to understand what eigenvalues and what eigenvectors. What eigenvalues and eigenvectors are. Yes, that is what I'm telling. Say, for example, then just do the A minus lambda with an 1 0 0 0 1 0 0 0 1 is equals to 0. Now solve for lambda, then you will be getting the eigenvalues. And for eigenvector, it has to be like it has to verify, because there can be like any number of eigenvectors. So if I just give an eigenvector, then I have to check that whether that is a valid eigenvector to corresponding to that matrix for with respect to a particular eigenvalue or not. That we can verify. Okay. Yes. So now there was certain sort of distortion here. So that is why I am using this one. But just remember the diagram of Bloch sphere. Okay. And the one who asks that whether why it is only z-axis, because again it is only the measurement axis, and the others are the way I can represent it, and it can like measure the, or it can be used to identify its position with respect to different axes. We can plot it, but ultimately we have to get it in the z-axis form, because only one axis will give me the measurement, because the Bloch sphere is a theoretical one, right? So say for example a ball is actually spinning. Now with respect to something you need to measure it, right? A ball is spinning, so if you check it with different angle, then it will be different outcome that will come to, that might come for the same observation. So at least you have to make a pivot with respect to the axis so that you can get exactly one output, or say more persons are doing observing the same thing, at least their observation will be correct. So in order to do that, we need to fix our matrix. Okay. Why theta by 2? Those who are asking, just solve it with respect to the graph given and check that why it should be a theta by 2. I'm not going to discuss it. The way we used to do it, the sine component and cos component, just try to solve and find that, okay, wherever this point, basically the blue arrow is pointing to, this is the position of the phi. So how I can measure it with respect to the cos component and like theta component associated with the cos or the sine. Likewise, just try to compute that what should be this, like the respective position of phi. So but this is just with respect to whatever theta I have, whatever phi I have. So this is a very general, representation of this psi. And also, yes, Arush, there is a website. There is a website where you can check it. But there is a website. It is only present in IBM, so you can check it. Maybe in the while we will be doing the lab, I can show you that you can actually see how it verify, like how to change the theta and phi, and how the different states, how it rotates in the Bloch sphere. It actually you can visualize that. Just check the like IBM quantum sphere, Q sphere it is called. You can see it. You can see it normally, or you can also watch YouTube for that. It's near simple IBM Quantum, or I will share the link later. I will share the link. Or you can wait, because in lab sessions anyway, we are going to do those things. Okay. Okay. So, and e to the power I phi comes in a similar fashion with respect to the position of the phi. But for our computation with respect to z-axis, the global phase has no impacts. That is why with respect to z-axis, so we will be ignoring it while computing. But it is a general representation which is very much useful if you are measuring it not with respect to z, that is with respect to any other matrices. Then this phi is very much useful. E to the power I phi. Phi is very much useful there. So alpha is equals to cos theta by 2, and beta is equals to e to the power I phi sin theta by 2. And just check whether it is like whether if we ignore the global phase, whether the normalization constraint holds or not. Yes, it holds, because cos squared theta and sin squared theta addition of them is 1. Now let us just put the values and see how the position, if we change the position, what will be the final quantum state, how it will look like. You can actually do it by changing just the values of theta and phi. You can have that idea. So just if you have theta is equals to 0, it will be like, just put the values, it will be get 0 only, because cos 0 is 1 and sin 0 is basically 0. Now similarly for, just a minute. Yes. So similarly for theta is equals to pi and phi is equals to 0, just try to put the value. So it will be cos theta by 2 times ket 0. Cos theta by 2 is ultimately 0. So that will cancel out. E to the power I into 0 is nothing but 1. So sine, it's sine pi by 2, which is 1. So 1 ket 1 will come. Okay. Likewise, you can check. So if say theta is equals to pi by 2 and phi is equals to 0, what will be your ket psi value? So it will be like, just try to put the values. Pi by 4 is, I guess, 45 degrees. So it will be 1 by root 2. So likewise, you can compute. Okay. Okay, now next concept was once we are done with the how a qubit look like, what is a Bloch sphere, and what is a generic representation of Bloch sphere. Some of you asked that why the theta by 2 is coming. I'm giving you as a homework. Just try to plot it through the geometry the way we used to do, that how that position can be found. Someone of you asked that the Hermitian thing. Just please refer more theories for the Hermitian. It will be very helpful. And that thing where you ask that how the different quantum states are actually on the rotating, or how by changing, these are the things that we are doing manually by changing the theta and phi. Definitely they are trying to change the values of theta and phi and check how the different quantum states are evolving, how it changes with respect to different color codes. Also you can see it, how you can do that kind of playing with the quantum states you have to do. So another one, we learned it theoretically. It's time to learn it more practically with respect to the mathematics. So it was no cloning theorem. So again, a brief introduction of no cloning theorem, because it's very, very fundamental to quantum cryptography. So no cloning theorem was when you just need a Xerox machine. So what I refer through a Xerox machine is by the term of a unitary operator, which is this thing. Where is my cursor going? Okay, this is this thing. This U refers to the Xerox machine that I was referring to. Okay, and ket 0 is a blank state. Why it is used? I need to insert a blank paper where I want my Xerox output to come into. So that like blank paper or blank state is ket 0, where to be cloned. Okay, tensor product, or say product ket phi using arbitrary, this is arbitrary state, that is the paper content that I want to clone. So it is what to be cloned. It is what to be cloned. It is what to be cloned. And U is a Xerox machine. Now that can give me two output. What output can come from the Xerox machine? The original paper will come out. So my initial ket psi will come out, and the blank paper will now be a cloned paper, which will be having the Xerox output, and that will come out. So ket 0 tensor ket psi will come, ket psi times ket psi. Okay, that is the definition of no cloning theorem. Now, now say if no cloning would have been supported by quantum mechanics, then what could we have? What could happen? Say, for example, I have two different arbitrary states that I want to clone. Say ket psi and ket phi. Okay, so these will be the two equations with respect to ket psi. I will be psi cross psi, and phi with respect to phi, it will be phi plus phi. So 1 and 2, these two equations I will be getting. Okay, now say for example, I want to calculate the inner product of ket phi, like ket phi, psi and phi. Okay, this is the inner product form. Now you know what is the meaning of this. Now here, just check it. I introduced a constant. Now in constant, for example, for a matrix, what is a constant? Constant is an identity matrix. For multiplication, what is a constant? Into 1. For addition, what is a constant? Plus 0. But in this case, what will be? How will a constant look like? Inner product of 0, 0, or inner product of 1, 1, or inner product of any two states that actually will yield the same thing. So that I have introduced, right? That I have introduced. Now, in the next line, I have written what? That is, this one I have replaced with a unitary matrix identity form, which is U dagger U. Can I do that? Yes, I can do that. So this is another one that I have introduced. So I have actually coupled this 0 with the left hand side phi, and the right hand side 0 with the right hand side phi. And in the middle, I have added another identity, which is a U dagger U. I can do that because any operator ultimately for quantum has to follow the unitary logic. It has to be unitary matrix. Okay. Now, Now, get psi, comma. Now this will be what? This u dagger 0 on, say, u dagger. It should not be 1, but identity matrix. No, this is the operator. Of course, I can do that. See, this is also a matrix. You are misinterpreting it. U dagger, U itself is an unitary matrix. I have told you that here matrix itself is an operator. Matrix and operator both are the same thing here. They're not different. And with I, it's not 1. It's an identity matrix. So if I want to write it equivalently, definitely I can write it. Both the things are same thing. Because I'm writing it in this algebraic form, but ultimately these are just the matrix expansion. If you just try to expand it in the matrix form, linear algebraically, you will be seeing the same result. No issue. So of course I can add whatever be my u, I can add the u dagger u. And 0, 0 I am adding as a foreign numeric constant, which is a scalar 1, that is 1. First I added 1, then I added u dagger u. Now I'm doing two things. Say u dagger 0 and this psi will give me psi and psi that I have written in the left. Just check from the definition of no cloning. U dagger 0 and psi should give me psi and psi that I have written. And on right it is u, and then 0 and phi should give me phi and phi. From my equation 1, I have done on the left hand side, and the equation number from equation number 2, I have written the right hand side part of the vertical bar. So now psi comma psi is psi basically, and then it's phi. So I can just write it in this way. This is get like within an inner product form, this psi comma phi square. Now when this will happen, when whatever I will have, say inner product of A will be equals to inner product of A square, or this will happen when I have either two matrices or these two are identical or these two are orthogonal to each other. Only these are the things that can happen. But these are not the cases, because my assumption earlier was that psi and phi, these were two different states, but my Xerox machine should work well for both the arbitrary states. That was my assumption. But here I'm getting certain contradiction. What is the contradiction? That, okay, my Xerox machine could have, as if my Xerox machine had worked only for one state. That is definitely phi and psi, they are identical. But what was my assumption? They are not identical. And what is the second thing? My second thing was that they are, what my observation is, that phi and psi, they are orthogonal. But what was my initial assumption? That I have to make the Xerox machine work for two different arbitrary states. Arbitrary means there should not be any correlation between the two states that I wanted for. So if it works for me, it should work for you, considering that there is no correlation between you and me. If a machine is able to do the same task for both of us, then only we can call it a Xerox machine, as if it should be able to clone me and it should be able to clone you. But right now I'm getting a form where it seems like either you and me both are same, or we are somewhere related to each other. But that contradicts our very basic assumption that it was two arbitrary states. So this actually gives the like symbol that none of the quantum states they can be cloned, considering if it is an arbitrary quantum state. Yes. Okay. Now, except this thing, there is another very important concept that comes from a little like changed with the no cloning theorem, which is another concept called teleportation. So we will be discussing teleportation and superdense coding during cryptography and communication. Just I wanted to give you a very basic idea here for teleportation, since it is another postulate for quantum computing. Teleportation is a technique where a quantum state from one point in the space, you can actually send it to another person in the space. It's kind of that. So in easy words, what is this thing? So here in teleportation, fundamentally, what is a teleportation? We call that it's very much related to telepathy. As if whatever I am thinking, you are also thinking the same thing. So does it mean that it's a cloning concept? It is not exactly cloning. Why? Because it is not exactly cloning, because it seems that will not be sending you the exact information, but definitely some information I will be sending to you. Now, so that you be able, with that information, you should be able to reconstruct what I have. But definitely that piece of classical information needs to be shared with you. So this is a concept of teleportation. Where, for example, why it is very useful for quantum is, say I have a state over here, a quantum state. I want to reconstruct the same quantum state. For that, what I will share is maybe I will be sharing a 8-bit key or 8 bits data packet to someone, maybe to any one of you. Okay. Now you are also like standing at the very basic level where you want to construct a quantum state and you want to construct the same quantum state. Now, I'm also here. Now, based on my construction and certain decoding logic, I will apply, and that particular piece of information I will send to you. Now, you will also do computation. Now, based on your computation and the packets, whenever it will be delivered to you, you will actually do a matching between them. And with a certain rules, then you will do a certain operation further on your obtained quantum state. So that ultimately you will be getting or yield the same state that I have. It seems a bit complicated or say abstract right now, that it can be done. So teleportation is the process where actually we do not state the quantum state directly, but we send some pieces of classical information from one point to another in order to create a quantum state at the other end. So, but those who are non-technical, they will understand it in a way that is a quantum state ultimately is being sent. But it is not a quantum state, rather it's a reconstruction of quantum state. And the decoding logic is somewhere like this. Say, for example, what is your 10th bit? Okay, if you are receiving in the 10th and 9th position, say 0, 0, please do apply this quantum gate. Okay, you are getting a 0, 1. Okay, then do not do this. Rather, make a phase inversion and then apply this quantum gate. Likewise, there is a set of rules or protocols that is attached to you that you will be having. Now, whenever you receive that piece of information, you will be starting your operation, and ultimately at your end, you will be doing the regeneration of that particular quantum state. This is also very useful. So how the technically this thing happens and whether we will be able to actually teleport something or not, that depends on how you proceed in the like communication and cryptography class. Now another very important part is a measurement in quantum computing. So what is measurement? Theoretically, so we have seen a few points that measurement is, first of all, a few points should come to your mind, that measurement is something which happens after we have everything done on the quantum state. So all the superpositions, everything, once everything is done, now whenever we are on the verge of obtaining the result, then we will be applying the measurement. This is the first thing. So say we have a superposition of states as input and a superposition of states as output. And suppose, say for example, we are calculating a function corresponding to multiple inputs at the same time. Problem is, despite of the fact that information regarding the value of the output resides into the register, we cannot extract all the information at a time. And one can only obtain the random results out of the set of results as output. I told you that even if you have a like 16 state superposed quantum register, if you try to measure it, you will be getting maybe one output or a fixed number of output, but what output you will be getting, that is not fixed, that will be random, that order will be random. So you cannot really have any control on that one. If you want to have a control, then just before your measurement, you have to do a certain operation so that it has to give you that result. So that kind of tuning you have to do in order to get your set of desired result. But if you do not do anything, if you leave it quantumly, no other operation, no other quantum logic if you apply, it will be any random output that can pop off. Okay. And hence extracting the desired information from a superposed set of output states is very crucial, and that forms the basis of measurement postulates in quantum computing. Okay. So defining the measurement operators in this way, I guess because of this distortion I have added here. Just a minute. Yeah, just check here. So measurement postulate is, for example, we define this 8 in this way. We have, say, a set of measurement outcomes is mn, m subscript m, where m can be 1, 2, 3, 4, likewise till n being all the possible results of measurement. Now, probability of obtaining then outcome M can be written in this way, that inner product of this psi, then M dagger MM, then again a ket psi. In that way, it's basically the expectation value. It's also called the expectation value, which is nothing but the probability of obtaining that particular outcome. So expectation value or expectation probability or only probability of an outcome, all the things are the same. So all measurement outcomes must satisfy the completeness equation. What does it mean? That all the outputs that you will be getting, all possible outputs and during measurement that you should be getting, it should satisfy the completeness equation. That is, it should satisfy URI. What does it mean? That is, say for example, you have 16 states. You can get one state. Now, if you do say all those measurements, that in the worst case, after all the measurement outcomes, it might be there that in 16 measurements you are not getting all the 16 states. Maybe few states are repeating, but it is just that your obtained state cannot be beyond any of the states that you have encoded into. So there has to be certain relation between the measurement outcome and the encoded inputs. In terms of, they cannot be more than anything extra or anything more than what you already have encoded. So that is how it has to be complete. And post measurement, your state will look like this. So whatever is the expectation value, root over of that on bottom, and on numerator it is MM, that is that particular measurement, the MF measurement times your state psi. For example, let us say, see, then we'll understand. Say for example, we have two basis states, ket0 and ket1, where M0 is this ket bra notation 0 0 and M1 is nothing but this 1 1. Okay. Say ket psi is an arbitrary state. Okay. So it is, say for example, alpha 0 plus beta 1. So the probability of having a measurement PM is this thing from definition. Just the same thing, like phi PM and phi. There is a probability of getting a measurement. Okay. So let me just write it down in this way. So P of 0 will be phi, then P of M is nothing but M0, which is 0 0. Right? This is a measurement. PM means the measurement M. You can also replace PM with M0. So it is basically, instead of an M0, I have written the ket0 and bra 0, and then phi is as it is. Now let me calculate this thing. So, okay, there is an entanglement. Just wait for a minute. Just wait for a minute. So say for example, I want to calculate bra this psi. Okay. So what it will be? Since my ket psi was alpha ket0 plus beta ket1, your bra psi will be alpha star 0 star, or say conjugate, whatever you call it, plus or dagger or plus beta star ket1 star. Just have this thing in mind. Okay. So equivalently, it means alpha star bra 0 plus beta star bra 1. And what was the LHS? Bra 5. And for ket, it is exactly the same in this order. So kets, because every like 0 star or ket bra 0 and 0 ket0, they are dual of each other. Bra 1 and ket1, that is also dual of each other. Bra psi and ket psi, that is also dual of each other. So whether it's a pure state or a like superposed state, they have that duality relation with respect to the bracket notation. Okay. So now say P0, now I want to calculate this thing, P0 equals to this. So just see what I'm writing here. So P0 will be, in case of bra psi, I'll be writing the value of bra psi that I have calculated here. So it is alpha star 0 star plus beta star 1 star. And here it was ket0. So I've just kept ket0 as it is. And here for this product, it is bra 0. I kept it as it is. And then ket psi, ket psi, where I have written alpha ket0 plus beta ket1. Okay, all these things I have written. Now, since alpha star ket0 star is alpha star bra 0 and beta star ket1 star is beta star bra 1. So if I just put the value here, I can see some 2 is by just mistake. Instead of 2, it will be star only. Okay. I guess here I made it beta square. Okay, just check it. It's obvious. You can check it. So P0 will be in place of this. Let me replace. So alpha star is alpha star. Ket 0 star is basically bra 0. And here it was already what it was. Here it is Ket 0. So I'm writing Ket 0 over here. So it's bra 0, Ket 0. I'm writing in this way as an inner product form. Can I write it? Of course, I can write it. The vertical bar, I'm actually marging it and just writing it in this way. Plus, it is beta star, this thing, then this is bra 1 and this is Ket 0. So bra 1, Ket 0 in the inner product form. And this one, the right hand, the right part, it was alpha. Alpha was here, is a scalar term, so I'm just bringing alpha outside. So alpha, here it is Ket 0 and bra 0 plus this beta and then Ket 0 and bra 1. I'm writing in this way. Now I have the entire resolved equation, where if you do the inner product, you will see we just have seen today, like bra 0, Ket 0, inner product, it will give you unity. Similarly, bra 1, Ket 1, it will also give you certain unity. And this another form where 0 and 1, they are like different. If you do the multiplication, you can check it, like bra 1 was 0, 1 in the row vector form, and Ket 0 is 1, 0. So it's 0 into 1 plus 1 into 0 ultimately, which is 0. So likewise, these entire factor will cancel out, and here also this entire like beta factor will cancel out. So it is alpha star into 1 into alpha, this alpha into 1, which is 1 into 1 is already 1. So alpha star into alpha, which is mod alpha square. So what is mod alpha square? P of P0. And what was P0? The probability of getting outcome 0. So now are you able to see through the measurement and the probability and probabilistic amplitude how all these things are related? So probability of obtaining 0 will be alpha square. Similarly, if you calculate, exactly similarly, if you try to calculate P1, which I would suggest, please do calculate this thing, it will be beta square. It will be beta square, P of 1. Okay. So is this part clear to all of you? Why the probability of obtaining a particular outcome where the psi is equals to, initially it was alpha 0 plus beta 1. Why it would be alpha and beta are probabilistic amplitude, and alpha square will be the probability of obtaining a 0. I had been telling this thing, like alpha square is the probability of obtaining a 0 and beta square is the probability of obtaining a 1. So how it is alpha square and how it is beta square, this is the proof for that. This is a proof for that. Okay. Okay. If you want, any one of you want, you can also do the checking for this thing with all the steps. Don't miss out any steps. Just perform all the steps and you can check it. Or also instead of an alpha on these things, you can actually take a 4 qubits or 2 qubit system as well. Say for example 0, 0, 0, 1, 1, 0 and 1, 1. Do the similar kind of thing. Do the similar kind of a thing for with respect to 0. Say for example, if I have 0, 0, 0, 1, 1, 0 and 1, 1 and say 1, 0 ka probability I want to calculate. So here what I have to put, instead of Ket 0, bra 0, I have to put say Ket 1, 0, bra 1, 0. Likewise, everything will be exactly same. And say the 1, 0 amplitude or coefficient was say gamma. So in that way, you would see that the probability of getting 1, 0 would be gamma square. With all the duality, bracket notation, all those things, just keep on resolving it, we'll be ultimately seeing the same output. That is a gamma square thing for 1, 0, Ket 1, 0. Okay, you can check it. And also repeating a measurement. So if I repeat a measurement on any state, that will give me the same state in which it collapsed in the first measurement, definitely. But if we change the basis after a measurement, based on the ordering of measurement, we will get the different results. Say, for example, in first case, we first measure it in the 0, 1 basis. And for those who just want ask that why it's z-axis, because in z-axis, we are actually have the pure states. So it is also called the 0, 1 axis or 0, 1 basis. All these things are equivalent. But other axis like x and y axis, that is basically the plus minus axis or some other like I e to the power I phi, all those things related to that. So we are unable to understand it from that basis that what measurement output we have got. Because we have encoded it starting from the 0, 1. So we start to measure in this way. But if our initial encoding would be in other like axis, then we can get the output in that axis as well. But generally we do everything with respect to the z axis because we start with the 0, 1 and 1 only. Those we consider as our pure states. Okay, so the case is if I just start measuring it in z axis or 0, 1 axis, then in the other axis, xy axis or x axis or xy plane, then say your outcome will be A. And if I start first measuring the plus minus basis and then the 0, 1 basis, then it is basically the outcome is B and A is not equals to B. So what is plus? Plus is also, plus means a superposed state of 0 plus 1. So plus is nothing but 1 by root 2 ket 0 plus ket 1. And minus is nothing but 1 by root 2 ket 0 minus ket 1. Okay, so how the plus and minus thing came into picture? Through the superposition. And this is just the naming convention. We call plus as a plus superposed state, which is ket 0 plus ket 1, and we call minus as a minus negative superposed state, ket 0 minus ket 1. But plus and minus are they are something related to the superposed or the mixed state. That is not with respect to the pure states. Okay, what is the time now? How the change of basis reflected in the state, change of basis reflected in the state. It is not reflecting the state, just reflecting the outcome that we are getting. What I'm telling is, if say for example, if you are measuring to a like similar quantum system, 2 times you are measuring it, whatever outcome you will be getting in the very first time, if you do not change the setting, in the second time also will be getting the same thing. But say for example, if first time you have a different basis and you change the basis itself, whenever you are changing the basis, then that particular outcome you will be watching. Now, once that particular thing will happen, then the z-axis with respect to that position, the angles will change. So depending on the angle, your final outcome will also change. Because you cannot do the measurement directly. For measurement, you will understand it. You will understand it in more detailed way when actually we will be looking into the measurements. Where first, if you have a 0, maybe you have changed it to say, applied certain Hadamard gate or quantum gate and made it a different one. Then you are measuring it. Then with respect to Hadamard, you are measuring and you are getting something. Then the vice versa will exactly not be the same as it would be if it is the same axis that you are using. So changing the axis sometimes might change your like state information as well. And depending on that, your measurement outcome will change. Okay, what is the time now? What is the time now? Do we need a break now or I can continue? Okay, 3:12. So I think we have only half an hour of time. So can I just, okay, break. Let me start then. Start after say, okay, continue. Let me have a 2 minute or 5 minutes will be more, I guess. Let's have a 2 minutes break, 2 to 3 minute break, I guess. What is the time now? It's 3:28. So let us all meet, say 3:31. A normal water break, tea break, whatever you want to. Just a 2 minute break, okay? Can I start now? Okay. Okay. So we do not have much time left. So let us start. Yes. So now we have a fundamental understanding of everything. So it's time we will enter into the real computing stuff. Okay. From right now till the last eighth for computing. Okay. And post that it will be some theory on ninth and 10, 11, 12 on some other topic. Completely different from these topics. So first of all, quantum gates. Directly to start with, first quantum gate that we have. Okay, first thing that what you should remember, that any quantum gate has to be reversible. If it is not reversible, if it is irreversible, it does not or do not suffice to be like quantum gate. That is the first logic. What is reversibility? That is, there shouldn't be any information loss. Whatever you do, it has to be like fully redoable, or you can actually, if you undo it, it will be exactly the same state where you end up, and it everything, the redo undo operation should be here with respect to the quantum gates now as well. Okay, for example, AND gate, I have told you, if you apply two AND gates, say, it will does not mean that it will again go back to the same state. Say for first AND, it will be for 0 at least, because 0 1 1 0 and 1 1, so there is no one-on-one mapping. But for quantum gate, it has to be a one-on-one mapping. That is the first thing, it has to be reversible, right? And also the second point is, whatever in classical gates you have, there is only one classical gate that is a quantum gate as well, and that is a NOT gate. No other classical gate is really a quantum gate, because of this lack of one-on-one mapping. If you find any other classical gate that has a one-on-one mapping, it also will be a quantum gate, or it can be used as a quantum gate as well. Okay, first thing. Second is, what is a NOT gate? Simple. N gate, you can check it over here. So N gate is basically a NOT gate, and it is represented in this way. The image is little distorted. It's basically kind of a XOR symbol. So within a circle, it is a like a vertical bar. So it's like a plus sign, not exactly the way we write XOR, XOR, the same way it is. It could be written the NOT gate. Okay, and NOT gate is basically can be represented with this thing, say 0 1 1 0 matrix for a 2 cross 2 matrix. And if you have a 0, so n of 0 will make it 1, and n and 1 will make it 0. Very basic thing. And ket 0 is nothing but 1 0, and ket 1 is nothing but 0 and 1. Okay, and this is also called inverter. Simple. Second one is controlled NOT gate. The images are a bit complicated here. I didn't get time to change these images actually. Just check it over here. It is not that issue. So in control NOT, it is basically kind of a XOR with a certain logic. What is the logic? Say for example, you have two inputs, A and B. So if you have 0 and 0, it will be 0 0. But if you have 0 and 1, it will be same 0 and 1. Now, if it is 1 and 0, it will be 1 and 1. Now, what does it mean? What is the third row means? In third and fourth row, you can see a different output of A and B, right? For both. It means that your A variable is the control variable, okay? And B variable is the target variable. Where whenever you have a 0 in control, there will be no change with the target variable. So exactly for A and B, whenever it was 0 0, it was 0 0 in output. When it was 0 1, it was 0 and 1. Why? Because in both the cases, A was 0. The control variable was 0. Bit is filled when A is 1, not filled, but bit is flipped. Yes, exactly. Bit is flipped. So whenever you have, in your control, you have 1. So you can see your 0 has become now 1, and your 1 has become now 0. So exactly the same thing we can represent in the diagram form also. Again, it's a bit distorted, but you will understand it. So it's just a filled circle followed by a NOT not gate in quantum, the way it represents, that is like a plus. So this is a symbol of a control not gate. And what is the field one means? Field one means a control. So on that particular qubit, you have certain control. Now, at least another observation you have to make is, see, control means at least you should have two inputs. Only on one input can you apply control? You cannot do. So this control not is the first fundamental two qubit gates that you have. Out of the two qubits, first qubit is the control qubit, second qubit is the target qubit. Got it? So this is the circuit form. This distorted one is the circuit form. This is the truth table form, kind of. Okay, or say function table, whatever you call it. And this on the bottom, it is the matrix form. Again, I'll be explaining what does it mean. Say, for example, just consider it column 1. Then it will be easy for you to understand. So here 1 means, what is the meaning of the first one? At the 1, 1 position, you have a 1. What does it mean? It means that whenever your 0, 0 is the input, say A and B, so what was your output? 0, 0 itself, right? So, and what is the cell for 0, 0 in output? This cell. So that is why you put a 1 over here. Similarly, let us check. Whenever you have a 0, 1, what output you should be getting? A 0, 1. And what is the cell for 0, 1? This cell, right? So here you are getting a 1. And similarly for 1, 0, for 1, 0, basically what is the corresponding value that you should be getting? 1, 1. But what is the respective position for 1, 1? This particular, say, row. So for this column and this row, it should be where the output should be mapped. Similarly, for 1, 1, it should be in the position of a 1, 1. Have you got it? So X is, say, for example, this matrix, any X I have represented. Once it has a 1, 0, it will be 1, 1. And once it has a 1, 1, it will be 1, 0. And also there is an alternate way of watching it. What is that way? Say, for example, the first row basically says that it is a 0, 0. It represents a 0, 0. The second row represents a 0, 1. The third row in this column vector form, sorry, not the row. The third column in this column vector form represents a 1, 1. And the fourth one represents, in the column vector form, represents a 1, 0. In that way also, either with respect to a row column, you can check, or directly in the column vector way. If you check any way, it will be the same thing. If you forget everything, don't use anything, just put it in the same way. That is for a 0, 0, where I should be putting it. So it should be 0, 0. If it is 1, 1, where I should be putting it, it has to be 1, 0. If it is 0, 1, it should be again 0, 1. If it is 1, 1, it should be 1 and 0. Simple logic. This is the first quantum gate, which is a 2-qubit quantum gate, and it is on this controlled logic. And in the circuit form, remember the field circle. Wherever on that particular line you will be watching a field one, that means that it will be used as a control. And that control line will only be activated wherever on A you are feeding the input 1. If it is 0, there will be no change on the values that you are getting from B. It will be exactly the same. But once you have a value 1 on A, your respective value will change. Also, just remember another thing that I want to mention here itself, that in the circuit, you might see that on bottom, it's a field circle, and top, it's just like a plus or a zone. Okay, that means nothing. That is not a wrong interpretation. That is not an inverted or anything. That just simply means then your B is the control and A is the target. Very simple. So how you will identify what is your control and what is your target? Through the whether it's a circle is field circle or it's an empty circle. If it is an empty circle with a plus within it, it will mean it is a target one. And if it is a field circle, wherever it is, it will mean a control logic. Control qubit. Someone has raised a hand, I think by mistake. Okay, great. So another gate is this thing, this Toffoli gate, which is in the circuit, in this kind of slide, you might see a lot of stuff. It is not that difficult really. It's a controlled NOT gate. So here you have two control or not. So the inversion will happen only if the two control, both the two controls are activated or they have the value 1. Now you just check the truth table or the function table. It is exactly the same. How you can identify which are the which are the, yes, I will be using pointer. So how you can identify from this circuit diagram? Can anyone tell that what is my control and what is my target qubit? Just write it on chat. From from the quantum circuit diagram, A and B is control. A and B, absolutely. Why? A and B is control and C is target. Why? Because A and B are field circles. Simple. And because it is controlled not, that means both A and B has to be one. So, and of course, because there is two control and one target, then definitely at least one thing is confirmed, that Toffoli or CC not or control not can never be applied until and unless we have at least 3 qubit system, right? On 2 qubits, it cannot work, or 1 qubit. So if I have 3 qubit system, then how many quantum states I can represent with 3 qubit? 2 to the power 3, that is 8 number of states. Just see, it's the logic, the way we are constructing things. So everything is like automatically you can derive. So out of ABC, I can have all these like 8 values, 0, 0, 0, 0, 0, 1, 0, 1, 0 till 1, 1, 1. Now, what are the two cases? What are the two cases where your A and B both are 1? Only the last two cases where I am using the green color basically. So just check both A and B are 1. When this thing happens, when you are having the value 6 and you are having the value 7, that is 110 and 111. So what you will do for those cases, which is your target? C is your target. So for that, in the output, where my cursor is going, in the output, just check it here for 1 1 and 1 1. I have not done anything, because nowhere like control will change, whether it's an input and an output, because control is control. So there will be no change in the control. There will be no change in the control, but only in the target, it will be like 0 will map to this 111 and 1 will map to this 110. On instead of the crisscross, you can actually write that 110 will be directly mapped to 111 and 111 will directly map to 110. Simple. And if I now tell you there is a controlled NOT gate, there is a controlled Toffoli, say for example, that means there is another control. Then of course in that case there will be 3 control gates and 3 control qubit and 1 target qubit. And when that will be flipped, you have to find out those cases where your A, B, C, all the values will be 3. If any of them are 0, you cannot really flip the target. Okay, simple logic. And now just check the matrix form itself. It's the same thing. Out of all these, for the first, all these values, there is no change for all the 6 values. This 6 cross 6 submatrix is just like an identity matrix. There is no change. Just check it. Only in this 2 cross 2 submatrix, where because you are dealing with these two things, it is a NOT gate. Just check it over here. In any way you want to learn it. See, this 0, 1, 1, 0 is basically what? A fundamental inverter or a NOT gate. And what was the NOT gate? NOT gate, how it looks like? A 0, 1 and a 1, 0. Just check. It is a 0, 1, 1, 0. So anyway, you can actually see the effect of 0, 1, 1, 0 here. For those cases where you are actually visualizing certain kind of a activation of the control. Okay, and alternatively, if you also want to see, say for example, 110 should be mapped to 111, so that's why here it is 1, and 111 should be mapped to 110, which corresponds to this cell. So here we are getting a 1. Is it clear? Absolutely clear. All these gates are like very fundamental. So we have seen NOT gate, C NOT gate, and C square NOT gate or Toffoli gate. Both are the same thing. Toffoli and C square NOT, they are same. Okay, in exam you might be asked a very basic question. Say for example, for a say a C to the power n NOT gate, C to the power n NOT gate, how many total qubits is you require? How many out of those qubits are controlled and how many out of those are target? I hope you are able to do that very easily. If it is C to the power n NOT gate or say C to the power n minus 1 NOT, whatever I write it, that's my choice. So from that value, you have to take that what will be the value in the control and the target total number of qubits. Yes, so likewise questions can come. If it is an MCQ question, likewise question can come. Qubit is starts from Q. Someone has written the C. Don't write C. I made the same mistake while I was presenting during my graduation, and I got scolded. That's why I told you. I started writing the quantum with a C, being nervous. Then I got scolded by my professor for that. Okay. This is another gate which also literally very theoretically exists, but it also kind of thought of to be quantum gate, but I have never implemented it, neither have used it ever. I do not really know that where what are the practical use cases of root over of not gate. Maybe there is some use case, maybe I have not got that one, but yes, you can actually, it is another gate which is also used. So this can work. Now, once this is a gate, means it is a matrix. Now, what will be the values of the matrix? If you do not want to remember, I do not know actually. Maybe that this can be a 6 gate. But what is the real applications of these gate exactly in the root n form? Maybe phase shift gate. For superposition, it is not really used. No. Superposition is something different. Superposition is not this one. Superposition is Hadamard, which is 1 by root 2, 1 by root 2, 1 by root 10, minus 1 by root 2. This is different one. The superposition is everywhere where you use that matrix. This is a different case. Okay. If you remember, don't remember the value, just put any arbitrary values of A, B, C, D times A, B, C, D is equals to 0, 1, 1, 0. Just solve for the values of A, B, C, D. You will be getting the value. Okay. That will be working. And if root n gate is applied on say another gate 0, which is 1, 0, just once you have the ABCD values, just put the values over here and got your root n matrix, which will be nothing but this thing. 1 by A will be 1 plus I by 2, 1 minus I by 2, B, C will be 1 minus I by 2, and D will be 1 plus I by 2. Once you have that, just put that value as an operator, and whenever it applied on 1, 0, which is a gate 0, you will be getting a certain quantum state again. Okay, so the 1, 0 is a quantum state which will evolve to this particular 1 plus I by 2 times gate 0 plus 1 plus I by 2 times gate 1. Yes, now comes the very important matrix, which is the basic essence of superposition. And unfortunately, there is no other gate available which can work for these superposition principle. So this is the only matrix that works. So Hadamard matrix or Hadamard transform is actually, yes, it is used to create superposition, and it is only operator or say matrix that will be used. Definitely, its order will be changed. A 2 cross 2 Hadamard will look like this. A 4 cross 4, 8 cross 8. Definitely, you can think of making them. So, this thing, just remember, uh, it should be good. It could be good if I just can write it down, or else if you follow, can every one of you can do just one thing, just multiply or just apply Hadamard on gate 0. Can any one of you do that? Just do the matrix multiplication and tell me what output you are getting. So question is, this is your Hadamard matrix. This comes from the Walsh Hadamard transformation and all those things. So that is something else. Those who are working with certain kind of a like communication or say that thing, let me tell you, the kind of phones that we used to have before this thing. So yeah, I cannot remember right now. It is used somewhere in the communication kind of thing for the code multiplexing or maybe something. For that kind of a multiplexing technique, we use it. Code division multiple access, I guess, if I'm not wrong. Just check it. So there also use the Walsh-Hadamard transformation to specify a particular code. Yes. So 1 by root 2, 1 by root 2, 1 by root 2, and last cell value is minus 1 by root 2. This is a Hadamard matrix, which is a 2 cross 2 Hadamard matrix. My question is just apply this Hadamard on gate 0. Gate 0 means column vector 1, 0. Can you tell me what is the output that you are getting? Can anyone tell me what is the output that you are getting? Okay, 1 by root 2, then 0, 1. Just the matrix form. In a matrix form, tell me, we get a column matrix of 1 by root 2. Yes, absolutely. Absolutely. So just check the column matrix now. I got it, Arush. Got it. So 1 by any way you want to represent it, ultimately it's a column matrix 1 by root 2, 1 by root 2. Just take 1 by root 2 as common, so it will be 1 by root 2 times 1 and 1. So what this thing is a representation of? This is a superposition, right? This is a superposition. So Hadamard initially was applied on what? Only on 1, 0, which was a column vector, which was basically a pure state called Kate 0. But once Hadamard is applied on this thing, what you are getting? 1 and 1 with certain amplitude, but you are ultimately getting 1 and 1, which represents a superposed state. Now just do one favor again for me. Just again on 1, 1 with a 1 by root 2, or take 1 by root 2, 1 by root 2 as a column vector. Again, can you apply the Hadamard? That is on the first output of Hadamard. I am telling you to again apply the same Hadamard. Now, can you tell me what is the output that you are getting? Just do the again another multiplication. Yes. Yes. So again, now you are getting a 1, 0. So what it was initially? It was 1, 0. Now you applied an Hadamard. So you got a superposed state, which was 1 by root 2, 1 by root. Now again, whenever you are applying this, you are getting a 1, 0. And 1, 0 in a column vector means it is Kate 0. So is reversibility verified here, or even for the one single gate? Can you check it? Yes. So always it will hold. Always your any quantum gate, the fundamental logic is it has to be reversible. See how beautiful it is. So 2 times applying an Hadamard is nothing but the same gate that you are getting. Now, just a small application of how these identities. So this is also called an identity. So each square is basically I2, that is a 2 cross 2 matrix, and it is an identity matrix 1, 0 and 0, 1. Now, say for example, where this is very useful is, say you have a long quantum circuit where different times and different times you have applied like twice some Hadamard gates for certain cases. But during the optimization of those circuits, often these things are replaced by an identity and we actually omit both the gates. And if I just increase, or if we increase a gate or some levels within the quantum circuit, or say very complex quantum circuit, the cost of that circuit increases to a greatest extent. So we should be using the gates in the most optimized form so that we can extract the maximum value out of it. Okay. So this is a Hadamard matrix. And also just one more thing, this is a 2 cross 2 Hadamard, but if we have a 4 cross 4 Hadamard, say, it will be in the submatrix form, that is 1 by root 2, 1 by root 2, 1 by root 2, 1 by root minus 1 by root 2 on top. Okay, right now I'm just telling you one thing. Say for example, a 4 cross 4 matrix is 4 row and 4 column. So first two row and 2 column is a one submatrix. Second one, that is just beside the first one, first row, it is another submatrix of 2 cross 2. On bottom left, it is another submatrix of 2 cross 2, and bottom right, it is another submatrix of 2 cross 2, right? That will like compose the entire 4 cross 4 matrix. Now for Hadamard, the top left, the top right, the bottom left, all are exactly the same 2 cross 2 Hadamard matrix that you can see on the screen. Only the bottom right position 2 cross 2 submatrix will be exactly the inverse of this Hadamard. Just exactly the way we have done here. Just see the bottom right position only has a minus 1 by root 2. So similarly, for the bottom right submatrix, 2 cross 2 submatrix Hadamard, for a 4 cross 4 Hadamard matrix will be minus 1 by root 2, minus 1 by root 2, minus 1 by root 2, and plus 1 by root 2. The same thing, just the inversion of whatever. Wherever it is plus, right now it will be minus, and wherever it was minus, it will be plus. Same thing. You can check it, no issue. Okay. So this is something that I thought of explaining. What is the time now? Let me check. I think just 4 minutes left. So I will complete it and I will just put these particular 8 questions as homework to you. So like tomorrow we will start with explaining these 8 first. We'll do manually all the calculations. Either I will just draw it and put it, or I will be using some paint tab and we'll be doing it. Anyway, all the solutions I will be giving to you so that you can do a check. And these kind of questions can also come. These kind of questions can also come. Just to tell you a brief meaning of this, say for example, in the question number 1, I have told you just a quick interpret so that you do not have any issue with understanding it. So initial state is state 0 for the first question. So now I am applying to Hadamard. So it will be get 0. Now you know it, but you have to check it manually. Okay, will not be given any quantum circuit where you can actually draw these things and can check what will be the output, at least for this exam. So second one is, first I have applied a kind of a plus, which is a NOT gate. That means whenever a 0 will come, it will make it 1. So the second question is basically we have to apply to like Hadamard in successively with an input 1. That is the meaning of this. Thank you. Thank you. I do not know how to like pronounce your name, but thank you. So 3 is first 3 represent the 2 lines represent 2 qubits. Now think very logically, try to do it. We will be anywhere if we are having any kind of a difficulty in understanding, that will be resolved. That is what I wanted. Okay, so 3 will be first 2 qubit. On first qubit I'm applying Hadamard, and on the based on the output of the first Hadamard applied on the first qubit, right now that I'm using as a control, and the second qubit, that was only nothing I have done. So but that value will be now the target one. So its value will be changed depending on the value of the control present in the due to the field bubble or field circle, whatever it is. Okay, and if anywhere you do not find that what state to start with, that say for example, say for 5, it's only like 3 lines and Hadamard at the end, that thing. Okay, so assume that I want you to consider 0. Ket 0 should be your initial state, not Ket 1 or not any other state. And also these particular gates, so I hope right now from these images you know Hadamard. What does it do? Only plus, it means a not inverter or a not gate. This is also what you know, C not gate or a control not gate, everything you know. Every time measurement will be in standard basis. Measurement will be the red axis. Measurement right now we have to do not do anything. Just before measurement, whatever is your like state of the quantum system. So how your quantum state will actually evolve, you can understand it through these examples if you solve it. So measurement is the last gate is measurement. And also one more thing, in 7th and 8th question, see, I have done something. What I have done is I have just merged the 3 measurement gates together. This is just a gimmick to show you that any way they can ask you question, or you might see in the papers. So both mean the same thing. Similarly, if we have a say 2 Hadamard for question number 7, I'm telling, they might give it, represent it with a 2 line, then a big box within that, they might write H. That also means the same. That means for both the gates, you have to apply individually Hadamard. So it is the same way. Once they are just using it, representing in whatever they form they want, they can represent it. That is the same thing. And for question number 8, I have used 2 CNOT gate, where qubit number 1 is control and qubit number 2 is target first. And then after some time, qubit number 2 was control and qubit number 3 is target. Then you are measuring. You should take the 2 by 2 matrix, right? Yes, yes. Ultimately, it is the same thing. Ultimately, it is the same thing for any age, because every time ultimately the meaning is on one single qubit you have to apply. On a single qubit, what is the matrix size that is applied? A 2x2 matrix. You just have seen. So exactly the same you have to apply. I'm stopping here. I'm stopping here. So we are on time as well.
Yes. Thank you, ma'am, for the insightful session. Ma'am has already answered the questions. So one more question has came up at 4 p.m. Maybe if you want to answer right now, then you can. Otherwise, we will keep it during the next session.
In 2q plus circle before H is which gate? Okay. In question number 2. Before H is which gate? Yes, I just told that that plus is the basically the inverter gate or the only not gate, the first quantum gate, only not. So in question number 2, it means nothing. That initially if nothing is mentioned, it is gate 0. But if you see this kind of a symbol, plus symbol, it is basically the plus here represents a not gate. So it means that you have to start with gate 1. That is a thing. It's not 0, it is 1 now. I guess Rohit asked this question.
Yes, ma'am. Thank you. Thank you for answering. So we conclude today, and the attendance as well as the recordings will be shared on the canvas very soon. Thank you. Thank you, ma'am.
and someone asked certain thing of related to entanglement, tomorrow while we'll be answering, we'll actually see entanglement. So one of the circuits actually possess a similar property of entanglement. Don't you worry. While you do it, you will be understanding. So instead of mine telling you, why don't you solve it and check that what resemblance with the maximum concept of a correlation and anti-correlation thing. Just do it yourself, you will understand. Solved example, I will be just solving them, and tomorrow I will be sharing it with you. But I just want all of you to do it once. Okay? Great, great. Thank you, thank you, thank you. See you all tomorrow. Thank you, thank you.